Good morning. Today we will discuss about special communication circuits. Special communication circuits. In that we will discuss about tuned amplifiers. Tuned amplifiers. So single tuned amplifier. So this is the hybrid pi equivalent for BJT. Single tuned amplifier, which is hybrid pi equivalent for BJT. Tuned amplifier. So tuned amplifier, it is a device which is used to amplify the particular or some range of the frequencies. LC circuit is used to band pass filter, which allows only some range of frequencies, which is act as the tuned amplifier. It is used in the TV remotes as it is changed the capacitance value, then corresponding channel will be changes. So they are widely used in variety of wireless applications. High frequency or radio frequency signals are amplified by using tuned amplifiers. When an amplifier circuit has its load replaced by the tuned circuit, such as an amplifier is called as tuned amplifier. The tuner circuit is nothing but a LC circuit, which also called as resonant circuit. When the reactance of inductor balances the reactance of capacitor, here when the reactance of inductor balances the reactance of capacitor in the tuned circuit at some frequency, such a frequency can be called as resonant frequency, which denotes by FR, resonant frequency. R is it is resonant, F is frequency. F suffix R, which is equals to 1 by 2 pi root of LC. Hybrid pi equivalent circuit for BJT. Here, the hybrid pi model, it is a popular circuit model used for the analyzing the small signal behavior of bipolar junction and field effect transistors. The model can be quite accurate for the low frequency circuits. A simplified version of hybrid pi equivalent circuit for BJT is given as. So here, these are the terminals marked as here C, B, E, which are collector, base, emitter. This is the collector, this is base, and this is emitter, and here this is the ground. And here we have R B dash E. Here this is the R B dash E, which is the input resistance. This is the input resistance, and here we have C B dash B, C B dash C. So here this is the collector to base capacitance, collector to base capacitance CB dash C, and here we have CB dash E, which is base to emitter capacitance, base to emitter capacitance. And here this is the resistance. So here this is the picture for the terminals, which is here marked as collector, base, and emitter. Already I told you RB dash E, CB dash C, CB dash E, which are input resistance, collector to base capacitance, base to emitter capacitance, respectively. And here this is the hybrid pi model of the equivalent transistor. And here we have input, and here we have the at output. Here it is GM, which is the transconductance, GM, which is the transconductance, and here VB dash E, which is input resistance, VB dash E, which is the input resistance, and here we have RB dash P, which is the extrinsic base resistance, extrinsic base resistance, and here we have RB dash E, which is input resistance. This is the input resistance, and here we have CB dash E, which is base to the emitter capacitance, base to the emitter capacitance. And already I told you GM, it is the transconductance, and VB dash it is the input resistance. So this is the hybrid pi model of the equivalent transistor. So already I told you these terms. RC it is output resistance, CC collector output capacitance, V8 is early voltage. Now the hybrid pi equivalent circuit, it gets name from the fact that circuit configuration is pi shaped. So the simplified circuit contains those elements that have most effect on the high frequency response. Here, next one, transconductance. Already I told you GM, which represents the transconductance. So transconductance, it is a function of collector current. So which is GM equals to IC by VT. GM equals to IC by VT. where VT is the voltage at room temperature T. IC it is the collector bias current. IC is collector bias current. Output resistance RC represents output resistance. So output resistance it is also a function of collector current. So RC equals to VA by IC. RC equals to VA by IC. Here VA it is known as early voltage. Already I told you VA is early voltage parameter of the transistor. Input resistance, the input resistance it is inversely proportional to GM. Input resistance is inversely proportional to GM. Input resistance RB dash E, which is inversely proportional to GM. Here B0 it is the short circuit current gain of the transistor. So input resistance RB dash equals to B0 by GM. Collector output capacitance. So it is an integrated circuit. This is the depletion capacitance of the reverse bias collector to subtrate isolation junction. Value of the function of reverse voltage. So value is small compared to the other circuit capacitance. Collector output capacitance. Collector to base capacitance CB. So this is the depletion capacitance of the reverse biased collector to the base junction. It is a function of reverse voltage. Base to emitter capacitance CBE. So this is the capacitance of the forward biased base emitter junction. It is to emitter capacitance. So CBE, this is the capacitance of the forward biased base emitter junction. It is the capacitance of the forward biased base emitter junction. So it consists of two components. First one it is CDPL plus DEPL, CDEPL plus CDIFF. So which is the depletion capacitance CDEPL. It is a function of the forward bias on the junction, and the diffusion capacitance it is a function of the transconductance. So CDIFF and CDEPL. So here the diffusion capacitance it is a function of the transconductance. So CDIFF which is equals to tau F into GM. Where tau F it is the forward transit time for the minority carrier movement through the base. Extrinsic base resistance RB dash B. Extrinsic base resistance RB dash B. So this is the resistance of the bulk base material. Resistance of bulk base material which effectively comes between the external terminal and the active part of the base emitter junction. Short circuit gain for the BJT in the CE. So here the short circuit gain it is a useful measure of the how a transistor behaves with frequency. And here already we have seen the circuit. Here it is RB dash B. We have RB dash E. We have already we have seen here RB dash B. It is the extrinsic base resistance. Extrinsic base resistance, and RB dash E it is input resistance. This is input resistance, and CB dash E this is the base to the emitter capacitance, base to the emitter capacitance. And here we have CB dash C, and here GM into VB dash E. Here GM it is transconductance, and VB dash E it is the input resistance. This is the transistor. This is the short circuit for the gain for BJT in CE. So here the transistor connected in the CE configuration which is shown above. So input or the base current is given as 1 by R equals to 1 by R B dash C plus 1 by J omega C B dash C plus C B dash E. Here that equals to 1 by R B dash C plus, and if you write this term like this, J omega C B dash E plus C B dash C, or R equals to cross multiplication 1 by R B dash E plus J omega C B dash E plus C B dash C. But VB dash equals to IBR, and VB dash equals to IB. R already we have this is the R which we have got. We have replaced here R with this term 1 by R B dash E plus J omega C B dash E plus C B dash C. or IB equals to cross multiplication, we will obtain IB equals to VB dash E into 1 by RB dash E plus J omega CB dash E plus CB dash C. So since the collector to the emitter is circuited, the output resistance and the capacitance of the equivalent circuit have no effect. The collector current ignoring the small current which flows through the CB dash C is given as IC equals to minus GM VB dash E. Hence the short circuit current gains AISC equals to IC by IB, which is if we substitute IC IB, we will obtain minus GM VB dash E by VB dash E into 1 by RB dash E plus J omega CB dash E plus CB dash C. So already we have got IB value. We have to replace this value here in the place of IB, and IC we have to replace with this term, so that AISC equals to minus GM by 1 by RB dash E plus J omega CB dash E plus CB dash C. The magnitude of the short circuit current gain is given as mod AISC equals to GM by root of 1 by RB dash E whole square plus omega square CB dash E plus CB dash C whole square, or GM by 1 by root 1 by RB dash E. So if we bring this one, root and square root get cancelled, so that we will obtain this one 1 plus omega RB dash E into CB dash E plus CB dash C whole square. So this one, which is equals to GM RB dash E by root of 1 plus omega square R square B dash E CB dash E plus CB dash C whole square. Let B naught equals to GM into RB dash E, or mod here AISC equals to B naught by beta naught by root of 1 plus R square B dash E omega square C beta dash E plus C beta dash C whole square. So this is plotted on the graph, and two important parameters can be identified. So these are the 3 dB frequency. Here this is the graph between omega beta and the unity gain transition frequency omega t. Here unity gain transition frequency omega t, and here omega beta, and here this is the curve. The 3 dB frequency. So it is the frequency at which gain magnitude drops by 3 dB from its maximum value. Here the frequency at which gain magnitude drops by 3 dB from its maximum value, so which is denoted by omega beta. So at omega equals to 0, AISC equals to beta naught. At omega equals to omega beta, mod AISC equals to beta naught by square root of 2. Already we have the value AISC, already we have seen this one. Mod AISC value equals to beta naught by square root of 1 plus R square B dash E omega square into C B dash E plus C B dash C whole square. So this is the value. So we can replace with this one. So here we have mod AISC equals to beta naught by square root of 2, and we will replace AISC value already, which I have shown you, so that we will obtain. So beta naught by root 2 equals to, this is mod AISC value. So beta naught by root of 1 plus R square B dash E omega beta square omega square beta into C B dash E plus C B dash C whole square. So here beta get cancelled. So we will have this square roots on both sides also will get cancelled, so that we will obtain this one 1 plus R square B dash E omega beta square C B dash E plus C B dash C whole square, which is equals to 2. So square roots on both sides get cancelled. So here omega beta square equals to 1 by R B dash E square C B dash E plus C B dash C whole square. So omega beta equals to 1 by R B dash E C B dash E plus C B dash C. So here square both sides we have square, these will get cancelled. So here omega beta equals to GM by beta naught into Cb dash E plus Cb dash C. So this shows that 3 dB frequency dependence on the transistor under short circuit output conditions. So, but even it gives a useful measure of how an amplifier using the transistor at the high frequency. Unity gain transition frequency. So this is the frequency at which gain magnitude equals to unity or 0 decibels. So let us consider this one. So so here we will equal to unity. Frequency of the gain magnitude equals to unity is nothing but unity gain transition frequency. So we will equate with the mod AISC with 1. So already we have this one. So beta naught by 1 plus R square B dash E omega R square. So C B dash E plus C B dash C whole square whole power 1 by 2, which is equals to, we are equating to unity 1. Or beta naught square far greater than 1, then beta naught square equals to this value 1 plus R square B dash E omega square R C B dash E plus C B dash C whole square. Or omega R square equals to beta naught square by R square beta B dash E C B dash E plus C B dash C whole square. Here R B dash equals to beta naught by GM. Already we have seen this one. So omega R equals to, just we are R B dash E, we are replacing with beta naught by GM. So omega R equals to GM by C B dash E plus C B dash C. So which is the independent of beta naught. Common emitter tuned amplifier. Common emitter tuned amplifier. So the common emitter amplifier with tuned output and input circuit is shown below VCC. So here this is the tuned common emitter amplifier circuit, and here we have C3 and C4, and here we have C3 and C4, which are DC blocking capacitors. C3 and C4 are the DC blocking capacitors, which have the negligible reactance at the higher frequencies, and these two have the negligible reactance at higher frequencies. And base resistors RB, we have base resistance, this one, bias resistance, this is the bias resistor, and here it supplies bias current to the base also, and it is also negligible. And signal sources are RS and IS, and here we have signal sources IS and RS. These two are the signal sources. And here in the hybrid pi equivalent circuit, RB dash B, which is the negligible. And here, if you see, we have CB dash, CCB dash, which is collected to the base capacitance. This is collected to the base capacitance. And here we have RB dash E, which is input resistance. This is the input resistance. And we have CB dash E, which is the base to the emitter capacitance, base to the emitter capacitance. And here this is inductance L1, inductance L2 here, and this is at the output side, and this is at input side. And here we have see here, this is the load resistance, and here if you see RC, which is the output resistance, load resistance, and output resistance RC, which is which are parallel here, and at this particular output side. And here this is V output, and here it is V input. And here if you see the output resistance of the transistor and load resistance, and this is RL and RC output resistance, and the load resistance of the transistor. So they are in parallel with the output tuned circuit. And here the output capacitance of the transistor, and here if you see the output capacitance of the transistor, which is parallel to the CC. And here these two are parallel to each other with the circuit tuning capacitance C2 here, and they will form part of the resonant circuit, and here they will form the part of the resonant circuit. And here we have GM, which is transconductance, GMBI, which is the transconductance here. Already we have discussed. And here this is the tuned amplifier equivalent circuit for the nodal analysis. So here we have input voltage, output voltage here, and here we have Y1, Y2, and GMVI, and here this is feedback YF here, and here GMVI, which is the transconductance. Let us discuss this one. So the components on the output side can be grouped together in the admittance form, which is Y2 equals to 1 by RC plus 1 by RL plus 1 by R2 plus J omega L2 plus J omega CC plus C2. Equivalent circuit in the figure can be analyzed. So admittance Y1 represents the admittance of RS1, RB dash E, and CB dash in the parallel with the input tuned circuit, and Y2 the output admittance. So feedback admittance YF already we have seen, which is equal to J omega C CB dash. So which is gives us 0 equals to GMVI plus V0 minus VI into YF plus V0 Y2. So this gives VI into GM minus YF plus V0 Y2 plus YF. We are taking common as here VI and V0 so that we'll obtain this one. So from this voltage gain, AV equals to V0 by VI, which is equals to YF minus GM by YF plus Y2. So to compare YF and GM, YF equals to J omega CB dash E, GM equals to value omega T CB dash E plus CB dash C. So at omega is far less than omega T and CB dash is far greater than CB dash C, then GM is far greater than mod YF. So therefore AV equals to minus GM by YF plus Y2. Therefore AV equals to minus GM by Y0, since Y0 equals to Y2 plus YF. So the gain is maximum when Y0 is resonant. Equation for input node is given as Y1. Hence the input admittance is YIN equals to IS by V1, which is equals to Y1 plus YF of 1 plus AV. So thus, to tune this to the resonance, the effect of the feedback must be taken into account. So YF of 1 minus AV is called Miller input admittance. So this one, YF of 1 minus AV is nothing but Miller input admittance. Now, common base tuned amplifier. So effect of the feedback capacitor CB-E can be nullified completely by connecting transistor in the common base configuration. So here the effect of the feedback capacitor CB-E, it is nullified. That means completely by connecting transistor in the common base configuration. So here CB-E, so here we are completely nullified by connecting here at common base completely by connecting transistor in the common base configuration. So here this is how CB-E. Here also we have, and this is CB tuned amplifier. Here V input, V output we have. Here they have given as F here, and capacitance C1. Here C4, and here C2, and here this is C3, and here this is the transistor, and these are the resistance. This is the tuned amplifier. So in this operation, LCB dash, it is parallel with the output capacitance CC, and it does not contribute to the input capacitance. So by applying a short circuit to the output terminals of B and defining the currents as shown, the short circuit output current is IC equals to minus GM VCB dash, and input current is IB equals to 1 by RCB dash plus J omega CB dash into VCB dash. Hence, the short circuit current gain for the CB amplifier is AIS equals to IC by IB, which is equals to minus GM by 1 by RCB dash plus J omega CB dash E minus GM by EB dash by 1 plus J omega CB dash E by B dash E. R, sorry, here this is R EB dash here, and by 1 plus J omega CB dash E RB dash E. So AIS equals to alpha naught by 1 plus J omega by omega naught. Here the 3 dB frequency for short circuit gain of the CB is omega alpha equals to 1 by R E B dash C B dash E. So where the 3 dB frequency for the short circuit gain, which is this one. So here CBE, which is equals to CB dash E, and CBE is far greater than CCB. So TEB is similar to the 1 by GM. Therefore, omega alpha, which is congruent to omega T, and AB equals to GM ZL. Then AB equals to GM R naught by 1 plus J by 2. So this is the available power gain. Available power from the source is given as PS equals to Vs dash by 4 Rs. Available power at output is P naught equals to I naught square by 4 by R naught, which is equals to I naught square R naught by 4. We are making this R naught to here. So power gain GAV equals to Vs dash by 4 Rs. Available power at output is P naught equals to PO equals to I naught square by 4 by R naught, which is equals to I naught square R naught by 4. We are taking this R naught to here. And then the power gain GAV equals to P naught by PS equals to I naught square RS R naught by Vs square. For both CB and CE circuits, I naught square equals to GM square VIN square. So GAV equals to GM square RS into R naught into RIN by RS plus RIN whole square. Cascode amplifier. The common emitter and the common base amplifiers can be combined to form an amplifier unit which is stable and has high power gain. So here in this cascode amplifier, common emitter and common base amplifiers can combine to form an amplifier unit which is stable and has high power gain. So combined unit is known as cascode amplifier. So here this is input and this is CE amplifier and CB amplifier. This is the output, and here this is cascode amplifier, and here we have CB, and here this is VCC, and here capacitance, and here we have this CB and CE here. So in this amplifier, bias components are omitted for simplicity. Both the transistors carry same collector current, hence we'll have equal transconductances. So effective load seen in CE stage is input resistance of the CB stage, which is alpha naught by GM. So this voltage gain of CE stage is GM alpha naught by GM, which is equals to alpha or slightly less than unity. AV is less than 1, which means that feedback will be insufficient to the cause oscillations. So voltage gain of CB stage is GM ZL. Hence overall voltage gain, it is alpha naught into GM ZL, which is equals to GM ZL. So the CB stage is inherently stable, so the overall amplifier is stable. Performance of the cascode amplifier has similar characteristics of CE amplifier, but with stability, and hence it is available power gain is high. Characteristics of the cascode amplifier. So cascode, it is a two-stage amplifier that consists of CE stage feeding into CB stage. Following are the characteristics of the cascode amplifiers: higher input-output isolation, higher input impedance, high output impedance, higher bandwidth. Thank you.